Hello, everybody. Today, our group is going to talk about the principles of momentum transfer and applications from the Jean Lopez textbook. So, in this first section, we're going to define the drag coefficient as well as the relationship between that and the Reynolds number, based off of depending on the type of flow happening with objects in an immersed liquid. So we have these three objects right here. We have a flat plane, which is right here. We have a sphere, and we have this streamline object. Basically, there's two key forces that we have to consider on these that will create some sort of drag based off of these objects' shapes. So then, right here, one of them is something called a skin or wall drag, which is basically parallel to the flow of the object relative to the surface. And then we have another one right here that will change based off of the geometry of the shape. It will curve around, which will impose like some acceleration and deceleration of the fluid on this object, which will help create more turbulence depending on the shape of this object. And this is what we call form drag. These two are basically types of forces that we have in the system that will affect the velocity of this stream right here. So we basically have this bulk velocity term right here of the stream before we get to the object, and then this will change relative here based off these lines, which we'll call like streamlines, which are the flows of the liquid. So then let's see, for the sphere, we have this based off this geometry right here, we'll have these like whirlpools right here, which we call eddies. And the one relationship this has is that this will result in the increase of form drag due to the shape of the sphere. So one way we can minimize it is have this come to a point. So we can reduce the form drag right here. So basically, we have these key forces, and then another point we can consider is something called the stagnation point, which is this right here in the center, where it looks like the streams are separating, going above and below the object, and the key characteristic here is that the velocity is 0. So some common chemical engineering applications of these systems is this could be used in a drying and filtration flow system, or we can also have a flow in tubes for a heat exchanger system. So heat exchangers as well. So these are some common uses that we might have. So then for these type of problems, we might want to predict the frictional loss and force on the submerged object. And then we have this right here, this layer right here, which is basically the boundary layer, which is where inside this is going to have a laminar smooth flow. And then we can basically use that. And at the edges of this, if we assume we go outwards from this, we can assume that we'll just have the bulk fluid velocity of V naught. And then we can also assume that we also understand that the tangential stress on the body due to the velocity gradient in the boundary layer we refer to the skin friction. So then the key takeaways from this is that we can understand the two key forces from this. We have are related to form drag and skin wall will serve as our net force for the system. So let's look at some equations. So this is an equation for drag coefficient, in which we have this force, the net force over area of the object, and we can rewrite this as the shear stress with this tau symbol right here. This is basically just shear stress. And we can rewrite this in terms of force if we want to. So we can use this for more practical applications or solving for force if we already know the drag coefficient. So if we rewrite it in terms of that, this will just be CD times bulk velocity over 2 rho AP. And then we look at the units for this. Makes the units a little better now. So we have our drag coefficient, our total drag force in terms of newtons, our area in terms of meters squared, and our velocity and density. So within this equation, what is the thing in this equation that is related only to the object? That will be the area, because each of these objects will have different areas and shapes. So, and with that, we'll have some different equations. So we have an area for a sphere, an area for a cylinder. Sphere is going to be pi, the diameter squared over 4, basically also analogous to pi r squared of the cross-sectional surface of the surface of the sphere. The cylinder is just going to be the length times the diameter. So it's going to be the surface area around the object. It'll be the surface area around the object where the flow is. Okay, and then we can relate, and the second component where we relate drag coefficient to find the properties of flow is something called the Reynolds number, which is basically the relationship of the flow. So we have like turbulent flow, we can have laminar flow, and if we have like something for laminar flow, we can relate this as some sort of friction factor right here. So then, let's say for laminar flow, we can drive a relationship that is this. And for Reynolds number, we will be using this terminology. So then we have 64 over the Reynolds number. This is something we use for a streamlined flow. Basically, it's a smooth flow from this case. And then we get an equation for that. So this is going to be the diameter times velocity times rho over this mu value, which is most representative of which is also a property of this shape as well. And we can combine these two into this g term as well. And then we can use this Reynolds number equation to solve for problems related to these shapes. So once we have these equations, we can use them to solve for flows past spheres, long cylinders, and disks within a submerged liquid. So if we remember, the relationship we're looking for is CD is the drag coefficient and the Reynolds number. And this is going to be based on the shape of the object and the orientation of the object. Basically, if it's like a plane side, if it's like basically what side of the object is the flow heading towards might affect the surface area that it's going to hit. So a key region we have is our laminar region, which is basically of a constant flow streamline of the fluid. Basically, the relationship between the Reynolds number and the drag coefficient is going to be linear. This is also what our boundary condition is, our boundary layer is. So our boundary layer is also this. But within this laminar region, we have a specific range within it, because the laminar region is not as big as the turbulent region, but once you have like a very small Reynolds number, like I'm talking about like less than 1, we can relate force with an expression called from the Stokes law, the Stokes equation, which is basically when force is equal to 3 pi mu diameter times velocity. So then if we use this equation and then if we equate this force from the drag coefficient, when we solve that for force, if we equate those two equations together, we would end up with something like this. And then we solve that for a drag coefficient. So that'll be dp E naught I over mu. And also within that equation, this is in terms of a sphere system, so I'm going to be using, because I know in that drag coefficient equation there's a area term as well, which I'm going to be using as pi dp squared over, should be 4. So I have that as well. And then basically this is how I end up with this relationship. But and then notice in the denominator, we see something interesting. This is the same expression as for Sorry about that. Same expression as for a Reynolds number, so I can rewrite this as 24 over the Reynolds number. And then we have this equation in terms of drag coefficient and Reynolds number, and then we can use this in terms of like a chart or a graph with experimental data and calculate these values. And then one other key thing is that if we increase the Reynolds number, we can have an increased separation in the layers, and then that's going to lead to more turbulence and wakes forming. So this is why we're looking at the relationship between the drag coefficient and the Reynolds number to determine the flows of the system based on the shape conditions, as we've seen, and this has been proven, and this is proven by these equations that we have. So we have a diagram like this. This is from experimental data right here. We are relating a drag coefficient and the Reynolds number. So basically, this area of the chart we have linear relationship between Reynolds and drag coefficient. This is going to be our laminar region. And then within this region, this is our Stokes region, which is where we use the 24 over, and this is where CD is equal to 24 over Reynolds number. And then this general laminar region, like outside of it, if I can draw this more clearly, the rest of the laminars region is basically, you can just use this as we have shown in the previous slide. Here we have an area where CD is constant, and then this ranges from 1 times 10 to the power of 3 to 2 times 10 to the power of 5. This is when CD is constant. So then, for example, if I have CD of a sphere, this is going to equal to 0.44. And then notice here at 3 times 10 to the power of 5, we're going to see a drop, which is where we're going to start seeing more turbulence. So this direction is more turbulence, and as we increase from here. So, and then some other CD values that we can have. And also another thing is that this is going to be constant as well. So so after this drop, we're going to have more constant values. So we can calculate the CD for spheres, cylinders, and disks if we like. So let's solve a problem with this. So I have a temperature value, a pressure value, flows past a sphere with a diameter of 44 millimeters. So we could just convert this off the bat to meters just to keep our units consistent. And then we have a velocity. We want to calculate the drag coefficient and the force of the sphere. So one thing we can start off with is we can calculate the Reynolds number. And this, we don't have our mu term or our density. So we can use the appendix. This is appendix A-3, A.3 from the book. At this temperature, we're going to get a rho value of, for air, 1.137 kilograms per meters cubed, and a mu value of 1.90 times 10 to the negative 5 PA times second. So then we can plug in all these values right here. And then we can get this relatively large Reynolds number. We know this is not in the Stokes range because it's now less than 1. But we do know it's in the first constant range before the drop. So, and then we did from that chart know that this is going to be around 0.44 for a sphere. So we can calculate that from the chart, and then we can plug it into our force equation, which is basically from the drag coefficient. We rewrote it in terms of force. And then AP, this is going to be in terms of a sphere, so this is pi d p squared over 4. Plug in the values. I think you can plug in the values from here. We should get a total force of 0.1833 newtons. If we do another example of a cylinder, this time we have the temperature this is water going over a long cylinder. we're going to find the force per meter length. So basically, this is the force per length. So we can take the length out of the equation, or we can just, like, for simplicity, assume that this is just going to be 1 meter. So we can just don't have to worry about moving these terms around. Okay, so from the appendix this time, this is A.A-3. The density of water is going to be 997.2 kilograms per meters cubed, and our mu value is going to be 0.9142 times 10 to the power of -3 pascals per second. So basically, we're going to use our same Reynolds equation, dP, velocity, rho, mu, plug in the values. We should get something around 9.817 times 10 to the power of 4. And then from the table, this is still from the same, within the same constant drag coefficient range. For a sphere, this time it's going to be around 1.4. This is for a sphere. No, not for a sphere, sorry, for a cylinder. And then we also know the area equation for this is also for a cylinder is L times diameter P, which is going to be 0.090 meters squared. Then we can plug this into our force expression. And then when we plug in the values, we should get a force around 62.82 newtons.
Hello. So I'm going to be talking about flow through packed beds. And over here on the left, we have an example of a packed bed. It's essentially a system that has some kind of solute in it or some kind of solid fraction that hinders flow. And because the flow here now has to travel through this solid fraction, it has to be described mathematically differently than unhindered flow. And that's what we're going to talk about here. And for a bit of an outline, we're going to start with some basic vocabulary necessary to understand the rest of the sections. And then we're going to talk about laminar flow in packed beds, and then turbulent flow, and then how intermediate flow is just the sum of the laminar and turbulent flows. We're going to talk about how the shape of the particles, so the particles here, if they're non-spherical, you have to account for that via shape factors. And then if you have multiple particles of multiple different shapes, you can account for that too when having a mixture of different particles. Finally, we're going to touch on Darcy's law for laminar flow in packed beds. So the first term we're going to define is the void fraction. So the void fraction is defined as the volume of voids in the bed divided by the total volume of bed. So the volume of voids in the bed, that's essentially this here. The volume that is not taken up by particles. So what's the free volume, the void volume, the volume that isn't taken up by anything? That's the numerator here. So that's the volume where nothing is actually present. And then the total volume of the bed is more straightforward. It's just the entire volume here of the bed. And this void fraction ends up representing essentially the percentage of the bed or the percentage of the system that's not taken up by particles. Intuitively then, if we wanted to describe the percentage of the bed or system that is taken up by the particles, we would do 1 minus the void fraction. So essentially 100% minus the percent of the void. And this yields the percent of the system that is taken up by the particles in the bed. Next, we're going to define the specific surface of a particle. This is designated AV. So we have to zoom in on a single particle in the packed bed. And then we have to take the surface area of the particle and divide it by the volume of the particle, and this will yield the specific surface of the particle. For spherical particles, it's easy to define the specific surface. You just take the surface area of a sphere and divide it by the volume of a sphere, and you'll end up getting 6 over the particle diameter. But for non-spherical particles, you don't know the diameter because it's not a perfect sphere. So you end up actually solving for the effective particle diameter as 6 over the specific surface in order to use this diameter in later calculations. We can now define the ratio of the total surface area in a bed to the total volume of a bed as the specific surface times the volume fraction of particles, or the 1 minus the void fraction. Here I've already shown the spherical particle ratio of the total surface area to total volume. Next, we define the average interstitial velocity v. Interstitial just means spaces between particles, so interstitial velocity just means velocity that flows through or around the particles in the packed beds. And it's defined as the superficial velocity based on an empty container divided by the void fraction. Essentially, if the void fraction was 100%, or there was no packed bed, there was no solid fraction of the packed bed, then the interstitial velocity would just equal the superficial velocity based on an empty container, because the void fraction would be 1. Next, we define hydraulic radius. Hydraulic radius is defined as the volume of voids over the wetted surface, and this can essentially be represented by the void fraction divided by the A we defined earlier, which was the ratio of the total surface area to the total volume. Finally, we can redefine the Reynolds number in terms of hydraulic radius and average interstitial velocity. Now that we've defined some terms, we can begin to discuss laminar flow in packed beds. We start with pressure-driven flow in a channel, as seen here. Then we rewrite in terms of hydraulic radius and interstitial velocity, achieving this equation, which theoretically describes laminar flow in packed beds. However, experimental data has shown that this prefactor of 72 isn't correct. The first reason that the prefactor is incorrect is this delta L represents the distance traveled through the system, essentially from one point to another. The minimum distance to get from one point to the other is a straight line, and that's what's used in this equation. However, due to the fact that there are particles in the system, the flow actually has to travel around them, which makes the actual distance traveled larger than the minimum distance traveled. Furthermore, the hydraulic radius predicts too large of an interstitial velocity, and we're able to tell with experimental data that the prefactor is actually 150. Using this new prefactor of 150 yields the Blake-Kozeny equation, which is valid for laminar flow where void fraction is less than 0.5 and effective diameter and Reynolds number are less than 10. We can follow a similar procedure for turbulent flow in packed beds, starting with this pressure-driven flow, which accounts for the friction factor. We can substitute in the average interstitial velocity and the hydraulic radius to yield, which still depends on the friction factor. However, for highly turbulent flow, the friction factor approaches a constant, and experimental data has yielded that 3 times the friction factor equals 1.75 for Reynolds numbers greater than 1,000. This ends up yielding the Burke-Plummer equation, which is used for turbulent flow, and the only limitation is the Reynolds number has to be greater than 1,000. We can also achieve an equation to describe intermediate flow, that is, flow that is not strictly laminar or not strictly turbulent, by simply adding the laminar and turbulent equations. This yields the Ergun equation, which when non-dimensionalized, we can see at high Reynolds number, or during turbulent flow, it reduces back down to the Burke-Plummer equation, where at low Reynolds number, it reduces back down to the Blake-Kozeny equation, making the Ergun equation valid for all types of flow in packed beds. Now that we've discussed how the type of flow impacts fluidized beds, we can talk about how the shape of the actual particles impact fluidized beds. Shape factors account for non-spherical shapes in fluidized beds. Here I've drawn an actual particle and then an equivalent particle, or a particle that has the same volume as the actual particle, but it's a sphere. From this equivalent particle, we can find the equivalent diameter, which is the diameter that yields a sphere that has the same volume as a non-spherical particle. From this diameter, we can yield to the surface area of this equivalent sphere and the volume of this equivalent sphere. We then define the sphericity shape factor as the surface area of the sphere with the same volume over the real surface area. Now we can redetermine the specific surface and the ratio of the total surface area to total volume in terms of this sphericity constant. And since we know the hydraulic radius is defined as the void fraction over the ratio of the total surface area to total volume, then this shape factor carries into the Burke-Plummer and the Blake-Hoseni equations, accounting for the non-spherical shape of the particle inside the equation itself. If a fluidized bed has more than one type of particle, you have to account for the different shapes of these particles through the mean specific surface, which is the summation of the volume fraction of a single particle times its specific surface. Then you redefine the effective mean diameter for the mixture as 6 over the mean specific surface, and this accounts for the different geometries of the different particles. Finally, we can describe Darcy's empirical law for laminar flow. We've seen that for laminar flow in packed beds, this equation is true, which shows that the flow rate is proportional to the change in pressure and 1 over the viscosity and the change in length, which is the basis of Darcy's law and corresponds to purely viscous flow in packed beds. That covers what I wanted to talk about for packed beds. Thank you for listening.
So for my section, we're going to be discussing flow in fluidized beds. I have a list of some of the topics that we're going to cover. First and foremost, we're going to talk about minimum velocity and porosity for fluidization. So basically, the velocity and porosities required for fluidization to be on set, and the relationship between those values and other values. Then we're going to talk about the relationship between the minimum fluidizing velocity and the pressure drop, and how we can calculate the pressure drop and the minimum fluidization velocity using certain values. Then we're going to do an example problem that will basically go over how to find the pressure drop and the height of a fluidized bed given a certain situation. Then we're going to go on and talk more about different cases of fluidized beds and how we can calculate the maximum allowable velocity for certain situations given different particle types and fluids with different Reynolds numbers. And finally, we will talk about applications of fluidized beds and specifically their usage in food processing and in the food and beverage industry. So first, let's discuss minimum velocity and porosity for fluidization. This is essentially the lowest possible velocity that is needed in order to create motion in the particles and for them to behave in a fluid-like manner. Because essentially, you will just have a bed of particles and then a fluid flow will be sent through the particles, causing them to rise and causing them to behave in a fluid-like manner. So here we have the Ergun equation, and as you can see we have delta P, which represents the pressure drop, and we have V prime, which represents the velocity. So by increasing the velocity to a certain amount in order to onset particle motion, you are also increasing the pressure drop. So we need it for the conditions for minimum fluidization, we need it so that the force of the pressure drop times the cross-sectional area of an empty bed is equal to the gravitational force on the particles, because this will cause the particles to begin to move, which is something that they won't do at lower velocities. So this minimum velocity for fluidization is denoted as V prime MF and is in units of meters per second, like typical velocity. And additionally, when we're talking about minimum porosity, it's experimentally determined and is denoted as epsilon prime MF. It's found experimentally because it's more dependent on the material that is used and is typically found using a gas stream rather than a liquid stream, because when you're using a liquid, it causes the value of epsilon prime MF to be larger than anticipated. So here we have this relationship between the height of the bed, the cross-sectional area, and the porosity of the material, where this value actually, the height times the cross-sectional area times 1 minus porosity is equal to volume. But here we have two different bed heights and two different porosities being compared, and this is a really usable and practical equation if you're looking to find different bed heights or comparing two bed heights at two different porosities or vice versa. So these are two really useful relationships that you can use in order to find different values. So here we're going to talk about the pressure drop and minimum fluidizing velocity and their relationship with one another. So this first equation, we have delta P times A, which is the pressure drop times the cross-sectional area of the bed, equal to LMF, which is the minimum fluidization height of the bed, times A again, which is the cross-sectional area, times 1 minus epsilon mf, and epsilon mf is the minimum porosity for fluidization. Now we have times rho sub p minus rho, and so rho sub p is the density of the particles in the bed minus the density of the fluid flow, and then times the gravitational force. And essentially, this is just the pressure drop at the onset of fluidization times the cross-sectional area, and equal to the buoyancy force times the gravitational force. And here buoyancy is expressed as the volume term that I mentioned previously, which is LMF times A times 1 minus epsilon mf. Then we have the difference in rho, and then times g, which, you know, buoyancy equals rho times v times g. So that relationship is shown here. So we also have this equation written in its SI form as well, which is just moving the LMF to the other side, and the area cancels out. So this is for like a very ideal case in which you have the specifics of your particle and you know your epsilon mf value. However, particles are often irregular in their properties, in their shape. In order to account for this randomness and irregularity of the particle shape, you can incorporate a term that is dp times phi s, which Victoria talked about in her section, which dp is the effective mean diameter and phi s is the shape factor. So by incorporating these terms into the equation, it becomes this super large equation, and is now in terms of VMF as well. And this equation can be further simplified by noticing that the highlighted section dp times v prime mf times rho over mu, which is the effective mean diameter times the minimum fluidization velocity times the density of the fluid over the viscosity of the fluid, is represented as the Reynolds number. So this term can be found also in the first term of this equation squared, so you can represent this equation as well in terms of a new assigned Reynolds number. But this equation can basically be used, given all of the other properties and values, to find the minimum fluidization velocity v prime mf. And also you can use the earlier equation on this slide to solve for the pressure drop, given your height of minimum fluidization of the bed and the porosity of minimum fluidization, as well as the density of the fluid and the density of the particles. And we will see how to do that on the next slide with our example. So now we will work on an example problem that will further our understanding of fluidized beds physically. Here we are asked to calculate the minimum height of the fluidized bed as well as the pressure drop at minimum fluidization conditions given this scenario. So solid particles with a size of 0.12 millimeters, a shape factor of 0.88, and a density of 1,000 kilograms per meters cubed are fluidized using air at 2 atmospheres and 25 degrees Celsius. The voidage at minimum conditions is 0.42. So here the important information is that we have a density of 1,000 kilograms per meter cubed, which is our density of the particles. We have that it's being fluidized using air at this specific pressure and temperature, and we're also given that the voidage at minimum conditions, which is our epsilon mf for the minimum fluidization porosity, is 0.42. So for part A, we are given that the cross-sectional area of the empty bed is 0.3 meters squared, and that the bed initially has 300 kilograms of the solid. And then we are asked to find the minimum height of a fluidized bed. So here, working it out and using the given mass, area, density, and epsilon mf, we can begin to calculate this L. So first, I used the density relationship of mass over volume in order to find the volume of the solid. So here you use the density of the solid, that's 1,000, as well as your 300 kilograms of solid, the mass, to find that the volume is 0.3 meters cubed. So then you can use volume over the area, which is meters cubed over meters squared, to find, in terms of meters, the height, which is 1 meter. So I'm going to specify that this is at a epsilon value of 0, as this is prior to fluidization. So this is the initial condition before the fluidization occurs. So then we use the relationship that we explained in the earlier slides, where the L over the LMF, which is the kind of initial bed height over the minimum fluidization condition bed height, equals 1 minus epsilon MF, which is your minimum fluidization porosity, over 1 minus epsilon, which is your epsilon equals 0. So then we can plug in 1 for L, 0.42 for epsilon MF, and 0 for epsilon, and find that LMF, so the minimum fluidization height, is 1.724 meters. So then, for part B, it asks us to find the pressure drop at the minimum fluidization conditions. Basically here, what we're going to do is that given this the 2 atmospheres pressure and the 25 Celsius, from an appendix in the book, we get that the density of the air is 2.374 kilograms per meter cubed. So now we can use the equation that I mentioned in the previous slide, which is the pressure drop equals the minimum fluidization bed height times 1 minus the porosity at minimum conditions times the difference of the density of the particle minus the density of the fluid times gravity. And if you plug in 1.724, which is what we got from part A, into here, 0.42 in for epsilon MF, and then the 1,000 kilograms per meter cubed minus the 2.374 kilograms per meter cubed, you get that the pressure drop is equal to 0.098 times 10 to the 5th pascals. It's also important to note that you can also find the minimum fluidization velocity using all of the information that is provided here. However, I chose not to include that part of the problem because ultimately it is just a matter of taking all of the information from the problem and just straight up plugging it into the equation that I mentioned on the previous slide that is in terms of the Reynolds number. So going a bit further, we can look at some more examples of fluidization. Firstly, we have that for small particles where the fluid has a Reynolds number of less than 20, you can use the following equation to calculate an operating velocity. And this equation is really valuable for liquids as you can also use it to estimate variations in the porosity. So then, moving forward, we can also calculate a maximum allowable velocity, which is the terminal settling velocity of the particles v prime sub t. This is calculated based on different operating ranges that are governed by the value of the Reynolds number of the fluid in the system. So for our first case, we have that for fine solids and where the Reynolds number of the fluid is less than 0.4, you can use the following equality in order to calculate this maximum allowable velocity Vt. So here, for example, if you were given that the Reynolds number was less than 0.4 and you were given a value of VMF, which is your minimum fluidization velocity, you could calculate your maximum allowable velocity. So additionally, you also have that for the case of large solids and where the Reynolds number of the fluid is over 1,000, you have a similar relationship in which you could also calculate your V prime T given that the Reynolds number is larger than 1,000 and that your V minimum fluidization value is given in your problem statement. So now I will discuss an application that I found to be quite interesting of fluidized beds, and this is their use in food processing. I honestly hadn't thought of these processes this way, so that's why I thought that it would be a really interesting thing to talk about. But in the Food Structure Journal, N.C. Shilton and K. Naranjan discuss how through a variety of fluidizing mediums, fluidization can be used in the food and beverage industry. So some of these processes include freezing, cooling and drying, heating and cooking prior to processing, and sterilization of products and treatment of byproducts. So many processes in food processing involve rapid transport to the material of interest, which in this case is the food. And since food particles are porous, fluidization is an excellent technique to achieve this rapid transport. So of this list, one of the main uses of fluidized beds in processing is for heating, cooling, and freezing foods prior to distribution and further processing. So this can be seen in a lot of, frozen meals that come already pre-cooked. They will be pre-cooked using a hot fluid, in order to fully cook the food, and then a cool fluid is used in order to cool and dry the food before it is frozen using an additional cold fluid. So Schulten and Naranjan actually mention how this process allows for food to be cooked without resources like oil. So this promotes the creation of foods with lower fat contents, and as well promotes the uses of less resources. Additionally, hot fluids can also be used as a method of sterilization in quality control, and this helps to ensure the safety of the products that are being produced. And lastly, here are the references that we used for our presentation. Thank you so much for watching.